Last time we had taken up hydraulic devices used in industrial control. I hope you will recall the two devices we had discussed in details. One, hydraulic linear actuator, and the other electrohydraulic valve. These are the two devices we had discussed. Electrohydraulic valve, as I had mentioned to you, is a proper interface between an electronic controller and a hydraulic actuator, which is selected on the basis of the power demand and other considerations. Now, let me take a system, a closed loop system today using these devices, particularly the hydraulic linear actuator. I will show that its use in industrial control is in abundance, and some of the very common applications will come before you. Here I have an example, a machine tool control example. You just see, it is very simple. Follow up the feedback principle in this particular example. This is the scheme which is used in practice. In this particular case, here is my workpiece. This is the workpiece, and this is rotated at a constant speed, and here is the tool. The idea is this, that the depth of the tool, you see that, please see the requirement, the depth of the tool should be controlled in accordance with the job to be done, and the job to be done is shown on a template. So, actually I want that this workpiece profile should exactly follow this template. So, it means the template is a command, and this command is to be reproduced on the workpiece, and in between I have this servo mechanism whose action we have to see. See, this requirement once must be seen. What is your standard way of saying what is command input? In this particular case, command input is YR. So, how do you set this YR? You set this YR on the basis of this template profile. I can say that this is my constant carriage speed. It means this whole assembly is moving at a constant speed. Please see, linear. This whole assembly is moving at a constant speed, which is going to set the command signal YR depending upon this profile. I can say that, well, there is a spring over here whose tension can be suitably controlled. Okay? This arrangement is there. Now, let us see how does this system work. Assume that in this particular case YR is set, but before I give you this description, I hope this you will recall. This is your power piston here. Here is a spool valve. This is your high pressure oil, and this is going to drain to the reservoir. So, these two are obviously the control ports. So, it means the oil to the control ports is going to be suitably controlled by the movement of spool, which is going to control the power piston motion and hence the load. The load in this particular case is the load of the tool, the associated friction, and how about the disturbance? Please see, the reaction force on the tool is going to provide the disturbance on the system, and the reaction force will depend upon the job to be done, the hardness of the material, and so many other factors, and therefore, the reaction force is uncontrolled and will act as a disturbance on the system. I repeat over here that as far as the load is concerned, the load is the mass m, the frictional environment for this particular movement B, and the tool reaction force, and the tool reaction force will be considered as a disturbance on the system. This entire carriage is moving with a fixed speed, and with this movement of the entire carriage, the YR position will change. The YR is your reference displacement for the tool. Okay? Now, please follow up the action. Yes, please.
Is it moving the y direction at the constant speed or?
The carriage?
Yes, sir.
Yes, it is moving inward in this translational way at constant speed. and that speed is the set depending upon the total the speed of response of the system. This is a constant rotational speed for the job. These points must be clearly understood, please, so that you get the feel of the system. This is a constant rotational speed for the job, okay, so that you get the profile all around. This is a profile only shown YR, and here you will be able to get this profile which is cylindrical in nature. So, this is the constant speed over here, and here is a constant carriage speed. It is not in the feedback mechanism. This or equivalently, you fix this and you move your template. It is you require the relative motion between the two, between the template and this particular assembly, so that YR can be set according to the profile. So, this is a way of giving an input, and one can have different ways of giving the input. In this particular mechanism, I have shown you, well, in this particular case, no, you will have to move this and not the template. Please see, because the tool is to move like this. The tool is to, any alternative which comes to your mind, please. Any alternative which comes to your mind, help me. Can I move the template and the job? Then I can keep the assembly constant. Please see, I will have to move the template and the job in a linear motion. Then I can keep this assembly constant, because I want this particular tool position, this particular tool to cut this particular job as per the template profile. Is this all right, please, with you? That an alternative arrangement is possible, but this arrangement works better. In this particular case, movement of this particular assembly is required. Yes, this assembly will move at a constant speed. So, in this particular case, please see, one point you must note, that is why I am making a mention power piston. So, it means the weight of this piston is going to be much higher than that of the spool. So, now help me, if suddenly a YR demand comes on the system, let us say from an initial equilibrium position, this let me say is the equilibrium position. From the equilibrium position, the YR demand comes on the system. What will happen? In that particular case, my claim is this, that this point will act as a pivot immediately, because this is a heavy piston, and the movement of this particular point immediately, instantly will not be possible. So, I will put it this way, that if this is the equilibrium position, these are the 3 points, and suddenly a YR comes, this is the YR demand, and the lever will take up this position instantly, because the power piston will provide a pivot to this, and the movement of the power piston immediately will not be possible. Okay? So, it means with respect to this, there will be an error E. Okay? Now, what is this error doing? This point moving in this particular direction, it means spool is going to move to the left. Help me please, what will happen? What will happen to this particular port? When the spool moves to the left, you find that this port is open to the high pressure oil, and this port is open to the drain. So, it means as soon as this moves to the left, high pressure oil rushes to the left side chamber of the power cylinder. I can say that this total unit is a power cylinder. So, if the high pressure oil rushes to this particular power cylinder, in that particular case, the power piston will move to the right, and hence a new equilibrium position will come where the forces will balance. And let me assume that the new equilibrium position is given by this diagram of the power piston. This diagram of this particular position of the lever. So, you can see that this is the net position. Y is going to move by this amount, E is going to move by this amount when YR is the input to the system by this amount. This point I again need your attention before I give you the mathematical model of this particular system. As soon as YR, because of this movement of the stylus, this is the stylus, this is the stylus please. As soon as the stylus movement on this template gives you YR, this particular point is going to act as a pivot, and hence the lever will move this way, pulling this particular spool this way. As soon as this spool is pulled this way, the high pressure oil rushes to this side, which moves the power piston this way, and hence there are two forces on this particular lever. One force is in this direction and the other force is in this direction. So, the net position of the lever will be given by the position where the forces appropriately balance, and hence I assume that this is the balanced position of the lever, and from here I see how the mathematical model can be obtained. The balanced position of the lever is given as this. You see from this particular diagram, A dash is this position and A dash, B dash, C dash is the new position of the lever. Let me say that I call this as position 1, this was the intermediate position, position 2, and this is the final position, position 3. These are the three positions. Look at this triangle now. If you look at this triangle, what I have done is C dash E, what is this distance divided by this distance is equal to this distance divided by this distance I have taken. So, what is C dash E? C dash E, as you find, is nothing but y plus yr. This is y, this is yr. And how about A dash E? It is A plus B, where A and B are the two dimensions of the lever with respect to the spool position. A and B are the dimensions with respect to the spool position. So, this is equal to, look at this quantity please, this quantity, that is B dash D is equal to yr minus E, should be clear from the geometry. Yr minus E is equal to B dash D, and about this distance is equal to A, and therefore E in terms of yr and y is given by this expression, and hence the lever is acting as an error detector. See, so far you have seen an op-amp acting as an error detector. So many other devices we have used, a potentiometer acting as an error detector. In this particular case, a mechanical system, a mechanical unit is acting as an error detector, though the constant of proportionality is not the same in this case. In this case you find the error E is equal to a constant k1 into yr minus another constant k2 into y, where k1 and k2 are different and they depend upon the geometry of the lever. I hope this is all right and it does not need any elaboration. I am going to use this particular expression, that is this error detector equation, in deriving the overall mathematical model of the system. If there is any question, I would like to welcome at this stage. Is it okay please? Fine then. Okay, fine. So, this error, if I write in this expression, this particular this thing can be written as this way. Here is an error signal E, I am putting a block over here B over A plus B, and here is the reference command yr. Here is a block which is A over A plus B, and here is a feedback signal y plus minus, this generates the error signal. This is what I am going to use when I give you the overall block diagram of the system. Okay? I hope this is okay now. Fine. Before I give you the block diagram, rather you should be able to do it yourself now immediately. See the action now again. The error E, let us follow the total signals. The error E has been generated on the basis of the reference signal yr and the feedback signal y. This error, what is the action please? You recall the equation, depending upon the movement of the spool and depending upon the pressure difference across the piston, there is going to be a fluid flow. Depending upon this particular movement E and the pressure difference del P across the piston, there is going to be a fluid flow. Recall the equation. The equation was K1 into E, where x earlier was taken as the spool movement and now it is E, the variable E, minus K2 into del P, where del P is the pressure difference across the power piston, is equal to, come on, let me see whether you recall, come on, recall from your memory. What is this expression equal to? K1 E minus K2 into del P is the total flow in the power cylinder, and this flow was taken as equal to Q equal to A into Y dot, where Y dot is the velocity of the cylinder, velocity of the power piston, A is the area. Okay, this was taken as A into Y dot, and another equation we had used, A into del P is the force on the power piston. This force is going to do the necessary job, and that is M Y double dot plus B Y dot plus F W. These are the two equations, and in addition today you have derived an equation, E is equal to B over A plus B into Y R minus A over A plus B into Y. That is all. These are the three basic equations which describe this particular system, and based on these three equations we can now draw the overall block diagram of the system. Please come on, please make an attempt for the overall block diagram of the system. This is Y R here, B over A plus B plus minus A over A plus B here. This is Y, I will generate it suitably. This is E signal here. Please follow through and tell me if there is an error. K1E, from here I am going to subtract A Y dot. So let me have an A here, and I will bring this signal from Y dot. Keep in mind, K1E minus A Y dot is equal to K2 del P. So what I do here, this I here put a block A over K2. This is going to give me a force. Look at the equations you might have written in your notes. If I have a block over here A over K2, this gives me the force variable. This I can have a disturbance variable at this point Fw. This is the net force which is being used to move the inertia against the viscous friction. So here in this particular block I can have 1 over ms plus b, this gives me Y dot. This Y dot can be picked up from over here, from here, and I can put it here, and here I have 1 over S, and this completes the total block diagram, please, which is identical to the type of systems we had, the type of block diagrams we had in electrical systems. You see that, as you know, the transfer function of a linear actuator is an integrator and a simple lag, Km over S into tau m S plus 1 we have derived, which is similar to that of an electric motor. As far as working of the system is concerned, its analysis and design, it is going to follow the same pattern, but the basic flow of information is different, the basic devices used are altogether different, and you must see what are those devices and how they are used in a particular application. Okay. Any question on this end, on this example, please, before I proceed further? Come on, say it loudly if there is a question. Okay. Fine then. Let us say that to just give you a feel of hydraulic hardware, this I take as the tool, and in this particular case I use an interface, the electrohydraulic valve, between the actuator and an electronic controller. Come on, the purpose now is, in this particular example we have discussed so far, there was no interface, the electronic controller to hydraulic actuator, in between there was no device. Now I am going to use a device, an electrohydraulic device, which acts as an interface between the actuator and the electronic controller. I feel there has been some problem in making the notes, it appears. You could make it, or there was any difficulty?
As the diagrams are complex, it takes quite a lot of time.
In that case, do you think that you could go to the library and take a look on it, or I should bring the Xerox copy of the typical drawings? Okay. Okay, I'll take care of it next time onwards. So in this particular case, please see, now I am making it, and hence there should not be any difficulty. I am making it just before you. In this case, this is the power piston, power piston, and this power piston I connect to an LVDT. LVDT. Now, into this particular power piston, let me say that I connect okay, let me say that to this piston I connect a servo valve, which is the hydraulic valve, and this is an electrical signal coming to this particular valve. And to this particular valve you require a hydraulic supply. You recall, you will have to recall the valve now, that you had a hydraulic supply to this particular valve, and the signal in this particular case was an error signal which was electrical in nature, and the output of this particular case was the spool displacement, the output of. So, these are the two control ports you see for this particular diagram. These are the two control ports. The complete configuration, the complete inside of the servo valve is not being reproduced. You look at the function of this particular block. An electrical signal, a voltage or a current signal is the input, which may represent, which normally represents an error signal. Corresponding to this electrical signal, you have the spool displacement, and depending upon the spool displacement you have the power piston movement, and this power piston movement is going to move this particular tool. Yes, I am going to complete it because the feedback path is not yet complete. I am going to complete this diagram now. Now, let us see that this LVDT, what is it is doing? Did we not discuss LVDT? I think we have discussed LVDT. LVDT is a device which gives you an electrical signal, an electrical voltage proportional to the linear motion of its core. You see your notes, you will find over there that we have discussed this device. This output of this device, if you recall, is a modulated signal. We can use an appropriate demodulator so that envelope is extracted. I am assuming that appropriate signal conditioning has been done, and I have an electrical signal which is proportional to the movement of the power piston, which is the core of this particular LVDT. So, I have an electrical signal here now which is proportional to the tool movement. Now, this electrical signal, come on, suggest the completion of this diagram now. Yes, wow, this is a feedback signal now which is electrical in nature, and I want to complete this diagram and make a suggestion what type of other device is required, so that this total system has now an electronic controller and a hydraulic linear actuator. Yes, please, come on, suggest some devices so that this particular diagram, this particular feedback loop could be completed. EH, electrohydraulic valve, I have already put. This is electrohydraulic valve. Servo valve I am putting is an electrohydraulic valve which takes electrical signal as the input and generates spool movement as the output. This I have already used. Electrical signal is the input and the spool movement is the output. Come on please, with the input given to you, you should be able to give an idea. Yes, a differential amplifier will do the job. This is an electrical signal here. What you do is, in this particular case, you have a reference signal which is electrical in nature. Whatever displacement is needed, for example, please see, your tool movement can be suitably programmed into a computer. Whatever tool movement is required, depending upon the profile of the job, this point may please be noted. This is what is done in today's numerical, computerized numerical control systems. Depending upon the profile of the job, you see, the tool movement can be suitably programmed. This is stored in your digital computer, and using suitable conversion of digital to analog signals, you can generate a voltage signal here, so that this voltage signal corresponds to the required movement of the tool. So, whatever may be your method of command signal generation, I say that This ER is a voltage profile which corresponds to the desired moment of the tool and hence which corresponds to the desired profile of the job. Here whatever job is to be done, it is translated into a, and the requirement of this is this, that this particular tool should follow this particular command which is which has been translated into a voltage. As has rightly been said, the feedback signal in this particular case is E naught, which is proportional to Y. This E naught is proportional to Y. Y is the movement of the tool, or which is the movement of the core of the LVDT. Now this signal has been generated, take away this, and this signal becomes the input to the servo valve, and hence this completes your electro-hydraulic control system, in which instead of lever, you see in the earlier case your lever was acting as an error detector. In this particular case, an operational amplifier is acting as an error detector. The advantage is not only limited to this, that a lever has been replaced by an operational amplifier. The advantage is much more than that. Actually, to have a suitable motion over here, you will require a suitable type of PID controller. Realizing a PID controller using a mechanical or hydraulic hardware is going to be less accurate and more difficult compared to an electronic hardware. So you will simply replace this amplifier, or you will simply enhance this particular op-amp circuit to include the necessary PID features which are required which are appropriately required for a control action. This point may please be noted. The advantage is not limited only to replacing the lever by an operational amplifier. The advantage really effectively comes when we come to the design of this particular system. This is not the design, this is only a layout giving you the total hardware configuration of the system. This is what will be given to you before you take up this design. That is, I am going to take one more hour, tomorrow's hour, on the hardware, and after that only the true job of the control engineer will start. You will find that with this hardware configuration available to you, your job as a control engineer will start, and you will have to design a suitable control function which will act on the error signal, and that control function is going to give a suitable control on the manipulated variable, so that the output follows the command without any transients and with as good a static accuracy as possible. Okay. So the interface of this particular electronic controller and the linear actuator through a servo valve is a very important feature when we come to actual design of the system. Okay. Well, I hope you got the feel of this, and the last phase of my discussion on the hardware is to give you some feel of the pneumatic devices also. We have discussed electrical devices, electronic devices, hydraulic devices, electromechanical devices, pneumatic devices, very much used in process industries. By process industries, I refer to the applications of temperature control, the pressure control, the liquid level control, the composition control, and so on. These are the applications which come under process control applications, and pneumatic devices are used in these applications quite extensively. Let us see the reasons. You see, one of the primary reasons is the simplicity. Well, air can be exhausted to the atmosphere, you do not need the reservoirs. Okay, is available in abundance, no problem of hydraulic fluid as you require in hydraulic devices. What else? What could be the other advantages? Probably non-inflammable is also one of the important advantages of the system. What else, please? Viscosity of air is negligible compared to that of hydraulic fluid, and the viscosity of the hydraulic fluid changes with temperature, and hence the performance of the hydraulic devices may change with the environmental changes. In this particular case, fortunately, that situation does not occur because viscosity is negligible. So, everything is really not rosy about the pneumatic devices, there is a problem. Hydraulic fluid is incompressible, therefore, the force wave can travel very fast, and that is why I made a statement that hydraulic devices are fast acting devices. While in the case of pneumatic devices, compressibility is a very important attribute, and because of this time delays occur, and therefore, pneumatic devices are not fast acting devices. I need your attention please, pneumatic devices are not fast acting devices because of the compressibility feature of the air. So, it is because of this you see the pneumatic devices are used primarily in these process control applications, because all these applications are slow in nature, and if these applications have got large time constants, if these systems have got large time constants, in that particular case on a relative basis pneumatic devices can be effectively used. Your attention may please be needed here. I need these devices are not used in motion control examples. For example, in position control you do not use because these are slow devices, but the process control applications are dominated by large time constant factors, and it is because of these reasons that the pneumatic devices are extensively used in these applications. Okay. One of the very simple device, though I have a slide, but I think I will make it, I will try to make, because otherwise you face difficulties. Most common device is this one. Please see, I am making a valve, flow control valve. I hope the picture may not be very nice, but gives you an idea. Let me remove it from here and give a packing here. Well, this is your fluid in, and this is the outlet of this. Here is a stem, the valve stem, and this is referred to as the back plate, and here is a diaphragm, and an error, this air signal here at a suitable pressure. Come on please, you can just see in this particular case you are simply controlling the opening of this particular valve. This is the control valve, the opening. This complete unit as a full assembly is commercially available, and this complete unit is so extensively used in the process control applications that your attention is very much needed over here, though we will make many approximations to model this particular device. So, in this case you just see the air pressure is the manipulated variable, the air pressure, this is the air signal coming. So, the flow is being controlled, the output flow in this particular case is being controlled by controlling the air pressure. This air pressure, let us say there is an increase in the air pressure. If there is an increase in the air pressure, then this particular stem will move down, and the movement of this is resisted by the opposing force due to spring. A balanced situation will come at which this particular stem will have its steady position. I need your attention please. When there is an increase in the air pressure, this particular stem moves down, and the balanced force, the balanced situation will come because of this spring. When this moves down, this particular stem, this opening is increased, and hence the flow through this will increase. The reverse section, if the pressure decreases, in that particular case, because of the spring action, this particular back plate will move up, and hence the opening will reduce, and therefore this flow will reduce, and therefore you can say that in this particular case, this particular valve is acting in such a way that the flow control, the flow here is directly proportional to the pressure at this inlet point. You can, the device is highly nonlinear, because the flow versus this pressure, rather flow versus the stem position and stem versus the pressure, these are nonlinear relationships. But if you assume, if you consider that your perturbations are small around the equilibrium point, around the steady operating point, then a linear relationship is possible, and you can say that if the stem position is given by x, if the flow is given by q, in that particular case q is equal to k1 into x, and x is equal to k2 into p, where p is the perturbation in the air signal, pressure of the air signal, and therefore I can say that q is equal to some constant k into p. So this air signal pressure is directly controlling the flow q of the control valve. Okay. Again, at this juncture I think I could raise a question: could you suggest an alternative hardware to realize this objective? An alternative hardware, you see, your purpose is to control the flow, and to control the flow you want to control the stem position, and to control the stem position you have an air signal. It means a suitable air pressure signal will have to reach this point so that the flow is accordingly controlled. So my question to you is this, that any alternative simpler arrangement which comes to your mind to control the flow in this particular case could be suggested. Yes. When I give you an example, you will say, oh, it was so easy. Surely you will say that. A solenoid. You see that in this particular case, instead of having this total arrangement, could you not move this particular stem with the help of a solenoid? Then where is the problem? Why not have a solenoid instead of this control valve? You see that when these control valves are very large, in that particular case the power requirement to move this particular stem is high, and solenoids normally are not able to provide that power, and the air signal, that is this particular device, is able to provide the required power. And in process control applications where large powers are required to move this particular stem, normally air operated control valves are used and not solenoid operated control valves. Okay. Any other alternative where the power requirement is also met with? Any other alternative, please? Recall your test problem. In that particular case, in the minor test, a problem was given wherein the valve was, instead of a linear motion, it was a rotary valve. So in that particular case, the required power was being given by an electric motor. So it was an electric motor operated valve. The error signal could go to the motor generates the appropriate torque, and that torque then operates that particular valve. The questions which came to your mind that day as to what is the load, please see that movement of this particular stem, the rotary in that particular example, the linear in this particular case, itself is a large load. In the process control applications, it requires large power, and this is the load which in that case electric motor was driving, and in this particular case this pneumatic operated device is driving. So it means this particular device has to generate suitable signal so that this stem is operated in a typical process control application. Okay. Again, you see, as we had in the electro-hydraulic systems, in hydraulic systems, your demand of hydraulic actuator was there because of the movement requirements, because of the mechanical motion requirements, and your demand of electronic controller is there because of realization of the control function. Same is the situation here. You see, you require a pneumatic signal, an air signal, because you want to use this pneumatic device for controlling this stem position. You do not want to use a solenoid. you want to use this particular device, while your controller is going to be a digital computer or an electronic device. So, it means in this particular case also you require a suitable interface between this particular device and electronic controller, and that acting on the similar lines is an electro-pneumatic transducer. The construction and working is so similar to electro-hydraulic valve that I can avoid the discussion, please. Electro-pneumatic transducer, I will give you the block diagrammatic description. So, this is the device. The input to this electro-pneumatic transducer is an electrical signal, and the output is a pneumatic signal, electro-pneumatic valve, sometimes referred to as electro-pneumatic valve. You see that this is again a must, you see, because if you want to cache on the power of digital computers or op-amp circuits for realizing your control functions, you really require a compatible device between the control valve which we have discussed and that controller. This electro-pneumatic valve will accept input signal, a voltage or a current signal, and an output signal which is a pressure signal. Now, let me give you some industry standards here. The type of electro-pneumatic valves available in the market. This is a device commercially available and we also have in our lab. This particular device, the typical signals are 3 to 15 psi. Pounds per square inch is the unit which is being used. Okay. 3 to 15 is the range of the output. It means in this particular case, the control valve is also suitably designed. After all, this is a total unit. So, the control valve, this particular backplate, the diaphragm and other components of this particular device are to be designed assuming that the input to this particular device is 3 to 15 psi, the signal which will be coming from an electro-pneumatic transducer. So, accordingly you see that it is a reverse designing. You require the range of flow, you should know what is the opening range you require here. Accordingly you design your system so that with the range of 3 to 15 psi with respect to gauge psi gauge pressure, you should be able to realize this objective. So, see this industry standard, 3 to 15 psi is a standard input signal which is coming to a control valve. So, this is a standard output of the electro-pneumatic transducer or the electro-pneumatic valve. What is the input? Input is an electrical signal, typically let me say, which could be in voltage or in current. So, now it has been standardized in the process industry to 4 to 20 milliamperes. So, it is for you to generate a suitable interface. If you have a voltage signal, if you have a current signal, convert it to appropriate voltage signal and vice versa. So, compatible voltage to current in converters will be required by you. So, the industry is going to provide you a device which accepts 4 to 20 milliamperes as the input signal and 3 to 15 psig as the output signal, and this is going to provide a suitable interface between the electronic controller and the pneumatic control valve to control the flow through a system. Come on please, if you have got this very well, you suggest the devices now for this application. Really, it could be a solution coming from you only. This is a heat radiator, please. I have given you in a tutorial class the arrangement of heating a chamber with the help of a heater. Now, I give you an arrangement of heating with the help of steam, and the hardware should come from you. A typical process control application, please. This is your control valve. This is the symbolic representation. Actually, it is the valve we have just now discussed. Symbolic representation is like this, that is, you are controlling the opening of this particular valve so that steam input could be controlled, and here is your condensate. Okay. So, heater replacement should be clear to you now. So, it means this is the heat going into this particular chamber. Okay. Come on please, suggest the devices. This is your continuously stirred tank reactor. Take the input flow, let me take it here, and let me take the outflow here, and here is your stirrer. Okay. Here let me say Q is the flow rate at a temperature theta I. The desired one, Q is the flow rate at a temperature theta. You want to control the temperature theta. So, you should give me the mechanism to set the value, the command value of theta. Theta I is a disturbance on this system. Theta I, the temperature variation of the inflow liquid is a disturbance on the system. I want to control this theta, and what is the manipulated variable? The manipulated variable is this control valve position, because controlling this particular position is going to control the steam and hence is going to control the steam flow rate. Come on please, suggest the hardware. I particularly want you to give me the flexibility of using a pneumatic control valve for controlling this particular position. So, if I proceed backwards, for example, suppose I have decided that I want to go for a pneumatic control valve. So, I think this picture is all right, I could take it here. So, here I have pneumatic control valve. So, please see, this is the, in this particular case, the stem movement, and hence it is controlling the movement of this valve. What is the input to the pneumatic control valve required? Input to the pneumatic control valve is a pressure signal P. Input to this pneumatic control valve is P. Now, this pressure signal P could come from electro-pneumatic transducer. Okay. This is the electro-pneumatic transducer over here. P, the range you must see is 3 to 15 psi, the industry standard. The pneumatic control valve is giving you the movement of the stem by X, and this X is controlling the flow Q. This X is controlling the flow Q. Now, this P is being manipulated with the help of an electrical signal. This electrical signal is the signal which is coming from a controller. The controller is an op-amp circuit. The controller in this particular case is an electronic controller which is an op-amp circuit. Come on, please give me this completion now. Come on, let us take the sensor point. Thermocouple, okay, we could take the thermocouple, though the alternatives are there. Thermistor and other things are there, but thermocouple is a very simple device. So, I am using a thermocouple here. The thermocouple will have to be interfaced to an appropriate signal conditioner, because this voltage may be too low, and secondly I need a current signal for transmission. So, this is a signal conditioner. Let me take this as a current signal. If it is a voltage signal, let me convert this to a current signal, there is no problem, voltage to current amplifier I can use. I can take this as a current signal, and the current range is 4 to 20 milliamperes. So, it means design of the signal conditioner will have to, now you see that in the process control application your design is regulated by these industrial standards. You will have, depending upon the thermocouple you are going to use, you will have to appropriately design your signal conditioner, so that the output here is 4 to 20 milliamperes. Now, this is going to be compared with a 4 to 20 milliamperes reference signal. Now, again suitable voltage to current amplifier will be required. This effectively is a voltage comparison, but in the block diagram there is no harm if I take it as a current comparison. So, this current here is your reference current which corresponds to your command signal.
So should this reference be to the signal conditioner, because otherwise the current range.
Now, since the signal conditioner constant will be known to me, okay, so as far as this is concerned, this 4 to 20 accordingly will be generated depending on, that is the signal, the generating device over here will be in such a way that the current requirements are met properly. 4 to 20, it means, yes, you are very right, the signal at this particular point after amplification has to be of this range. So, this total system will be designed to meet that requirement. Total system, you are very right, the design of signal conditioner will be guided by other devices as well, otherwise it may exceed this value, and this comparison over here is done in this error detector plus minus, and let me say that I have an amplifier. I am taking all in terms of currents, suitable voltage conversions and comparisons are possible. So, this is an electrical signal to the electro-pneumatic transducer which is generating the appropriate pressure signal, and hence this becomes the total device which is very much in use in industry as far as process control applications are concerned. I think I may not be too wrong in making a statement that almost all the applications today are being controlled this way through a pneumatic control device here and an electro-pneumatic transducer interfacing this device either to an op-amp circuit or a digital computer. If not all, most of the applications are having this type of hardware. Thank you very much. Yes, please.
So you said like in devices where you use pneumatic control, roasting the slow. So what about cars where you have power brakes? That's what pneumatic isn't it?
Which device?
Cars which are power brakes, not the hydraulic brakes, the air brakes, the power brakes. So then,
It depends, you see, most of the devices, most of these automobiles have hydraulic brakes which are fast
buses and
acting.
trucks have only power brakes, not air brakes.
No, it depends. I mean, you have to see the total action required. The total. Yes, compared to the hydraulic or electrical devices, they are slow acting. In comparison, they are definitely slow acting. Correspond compared to electrical or hydraulic devices. Okay.